Okay, this is for my Calculus 1 optimization lab number 1, and I'm going to start and do a video for each one of these, or maybe get two in a video. So this is our first lab, first problem. So it says a rectangle has a perimeter of 100 feet. What length and width should it have so that the area is maximized? So the first thing I want you to look at is I drew a picture of a rectangle. And we all know that a rectangle has opposite sides, congruent, and parallel. So you get to label this however you want to label it. So I kind of labeled this because this is in the X. This looks like this is how the X-axis looks. This is how the Y-axis looks. I know they're both congruent and same, so I can set that up. They tell you it has a perimeter of 100 feet. So we're going to set up this problem like I have you do in class. And what I want you to do is write the constraint first, and then the objective, because I think if you get used to doing it this way, it just helps you organize your thought. Well, what is the constraint? Well, the perimeter is our constraint because they told us, okay, that we had to have 100 feet of the perimeter. So the perimeter is our constraint. It's 100 feet. That's all we can have. The objective is they want max area, the maximum area that we can have with 100. Okay, so that is our objective. Okay, so you can label your picture any way you want, but you have to use what you have for variables in your equation. So the first thing I said, all right, our constraint equation is perimeter. Well, perimeter is all the way around. So I said 2x plus 2y in my picture has to equal 100. There's my constraint equation. My objective is the max area. So I know area is length times width, or base times height is going to be in my picture x times y. So now I have my equations. Now I'm going to go through on my constraint and solve for one of the variables. So I solve for y. So I'm going to do 100 minus 2x, go through and divide everything by 2. I get y equals 50 minus x. Okay? I have now written y in terms of x. You take this right here, and we're going to plug it right into the y spot here so that our area is going to be in one variable in terms of x. So I have x times 50 minus x. So the area of our rectangle, which has our constraint in it, is going to be 50x minus x squared. Okay? Now remember, I want to know maximum area. So you have to, basically, we've been learning this, you take your first derivative, put it equal to 0. That will tell you the x that yields the max area. So this is why I'm going to do a different color, because I'm trying to get you guys used to this, is you're actually going to do a prime, you're going to do the derivative and put it equal to 0. So it's the power rule, 50 minus 2x. And we're going to put that equal to 0. Then I'm going to go through and solve this. So I'm moving it over the other side. I have 2x equals 50, x equals 25. They didn't give us any units, so that is what x is going to be, because I always start you out simple. Before you go further, over here, you need to do your first derivative test. And what we're going to do is check to see if 25 is really a maximum. And that's what they want to know. So you're going to, this is just a number line, guys. 25 is, and this is my A prime bar, is I'm going to look to the left of 25, to the right of 25 to see if this is truly a max. So if you look at it right here, our first derivative, and you can put this in your calculator if it makes you more comfortable, is here, if I go to the left of 25, we'll say 20, that'd be 50 minus 40. I'm going to get a positive number. Okay, that's what we're testing for, is see if it's a max. If I go to the right, we'll say 30, you'll see that it will be negative. Or you can graph it and look at your table and look at the signs. I see this is truly a max, so I've tested it with my first derivative test. Please don't forget the first derivative test. It's like the most important thing. Okay, you're testing to see if it truly is a max, because there's going to be times where you have more than one value, and I start you off simple with just one. Now I'm going to actually figure out what my y would be. So I'm going to do 50 minus 25, or y is 25. Now you're like, but that's not a rectangle, that's a square. Well, a square is a rectangle. And as you start to do optimization problems, you'll see that the closer you are to a square or a circle is where you have your maximum. So basically, this is a square, 25 all around. And we used calculus to determine that. Okay? Let's try number 2. Yeah, I can get 2 in this video. That'll be good. It says a dairy farmer wants to fence in a rectangular pasture adjacent to a river. So here's my river. So pretend we're God. We're looking down here. And he wants to do a pasture, but he's only going to have to do fencing on 3 sides. I actually should have drawn this before I started. Okay, so here's the fencing. And just think that we're God looking down at it, okay? And here's my river. It's right here. Okay, so the river's here. They're going to fence off this rectangular pasture. It's important that it's rectangular because that gives us certain properties. The pasture must contain 180,000 square meters. So when they tell us that, that is area. They're telling us the area has to be 180,000 square meters, okay? I always look at the units to make sure. In order to provide enough grass for the herd, what dimensions would require the least amount of fencing? So we're looking for the least amount of fencing. And right here is, because I get to play with colors, is all the grass for the herd is inside here. Okay, so there's our pasture. Okay, so let's set this up like I always do to organize your thoughts, excuse me. So I have constraint and objective, and I'm going to actually label this. I'm going to call this, you actually could do either way. I'm going to call this X's here and a Y here. You could go the other way around, or you can call it L's and W's. And I notice that my constraint is going to be my area, all right? So the area of the pasture is my constraint, okay? The objective is the minimum amount of fencing, okay? Minimum amount of fencing, which if you were to look at a rectangle, is going to be the perimeter of those 3 sides, okay? So let's first of all do our area constraint. I know the area of this is, according to my picture, X times Y, and they told me it has to be this, so I have X times Y has to equal 180,000 square meters, okay? My objective is going to be minimum fencing. So let's just call it F for fencing. So what do I have for fencing? Well, I'm just going to come around here, here, and here. So I have 2 X's plus Y, right? So now let's go through and do this. I want to get this all in one variable. So over here, I actually solve for Y. So I have Y equals 180,000 all over X. And then you guessed it, I'm going to take this constraint and put it right here in the Y spot so that I can figure out what my my minimum fencing is going to be. So I have my fencing is going to be 2X plus 180,000 all over X, okay? And I got my equation. Now I am going to write it like this, and you'll see why in a minute, because if we're looking for a minimum or a maximum, we always have to do our first derivative and put it equal to 0. So by me writing it this way, I didn't quite finish, I got so excited to write that, it's all set up to do the power rule. Okay, so I'm going to change my colors here just so you realize right here is where we change and we start doing the derivative. So I'm going to do F prime is going to be 2, ready, minus 180,000 X to the negative 2. Put it equal to 0. What I would suggest to make this a little bit easier to solve, because everybody starts freaking out, like, how do I solve that? Write it like this. 2 is going to equal, so I'm going to move this whole part over on this side, 180,000, so it turns positive, and I'm going to write it and put it down in the denominator, because it makes it a little bit easier to see what we're going to do. So I just basically rewrote this, put the X and negative 2 underneath here, and then I just moved it to the other side. Then you can see, I can cross multiply. 2X squared equals 180,000. Divide through by 2, I get X squared equals 90,000. Okay, then I'm going to take the square root of both sides, and truly it's plus or minus, but since we're talking fencing, we only need to look at the positive. So x is going to be 300, and this was in meters. It's going to be 300 meters. Okay, now right adjacent to this, I want you to do your first derivative test. So we're going to set up our f prime bar right here, and we're going to put 300 right here in the center, and we're going to go to the left and the right. So I kind of have it right here for you. So let's circle this right here. So if I go to the left, and you can move it back over so you can see, or you can even check here, either way, that when I go to the left of 300, we'll say 200 or whatever, or 100 you could use, you're going to see that you're going to get negative numbers here. If I go to the right of 300, I'm going to get positive numbers. Therefore, this is my first derivative test. This is a minimum. So that is the minimum for the fencing. So now I can go through and say, okay, I know what y is going to be then. Y is going to be 180,000 divided by 300, or if you will, y will come out to be 600 meters. Okay? So they just said what dimensions. So the dimensions that I would need for this pen or this pasture fencing in is 300 meters by 600 meters. So right here on my picture, this is 300 meters. Here's 300 meters. And the 600 meters will be here. They all add up to our minimum fencing. And then if you did the area, that would give us that area. So I hope that helps with these two problems. I'll do more for you.